Warning: the video you're about to watch contains mathematics at the level of pre-calculus. All material has an assumed prerequisite of college algebra and trigonometry. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. In this video, we're going to continue our conversation about division of polynomials. So the last video you should have watched is all about synthetic division. You kind of need, well, not just kind of, you definitely need that to be able to understand where we're heading in this video. Not only that, but you need the division algorithm. And just to remind you, the division algorithm just said if you have a polynomial p and a polynomial d, p is called the dividend, d is called the divisor. Well, when you make that division of p over d, you get a quotient, q, plus a remainder over that divisor. And that theorem we did not prove. However, that theorem can be proven. I just didn't want to prove it in the video that we went through. But that is going to be what we're going to rely upon heavily in this section. And so the very first thing we're going to do is deal with something called the remainder theorem. The remainder theorem ends up being incredibly important, and it gets often overlooked by students and instructors alike. However, it's a great way to evaluate a polynomial. And yeah, I'm sure you're probably thinking, well, I could just plug in a value. If you want me to find out what the value of a polynomial is at 10, for example, I could just plug that in to the polynomial. It is absolutely true. Yes, you can do that. However, there's a secondary way of doing that. And that is by using the remainder theorem. So the remainder theorem tells us that if we have a polynomial and we divide that by the linear factor x minus c, then the remainder of that division is actually the value of the polynomial had you just plugged c in. So before I go into the proof, maybe in a different color here, I'll just showcase what I mean by that. Suppose that you have a polynomial p of x that is equal to, it doesn't really matter. Let's say x cubed minus 2x squared plus 3x plus 4, right? And let's pretend that you want to evaluate that at 1. Well, obviously, you could just plug 1 in. You get 1 minus 2 plus 3 and then plus 4. And that is pretty simple. 8 minus 2, which is 6. Very, very easy to do. However, suppose instead that you took that p of x and you wanted to divide it by x minus 1. What would that turn into? More specifically, what would the remainder be? Well, we know that if you divide from the last video, we know that if you want to divide by the linear factor x minus 1, you can always use synthetic division, where in this little spot here, we put the 1. I'll put the coefficients of our variables here. So 1x cubed minus 2x squared plus 3x to the first plus 4. And you bring down the 1. 1 times 1 is 1. And negative 2 plus 1 is negative 1. 1 times negative 1 is, well, negative 1. 3 plus a negative 1 is 2. 1 times 2 is 2. 4 plus 2 is 6. And I want you to notice that remainder, remember, we said this last time, that when you do that division, you will get 1x squared minus 1x plus 2, and then plus the remainder over the divisor. Notice the remainder is 6. And notice that's what we would have gotten, or would have arrived at, had we just plugged in 1 into the polynomial. So let's go ahead and prove this theorem, but there's something super powerful about this. So if I want to evaluate what the impact of this is that if you want to evaluate P at any number, instead of just plugging in that number, which seems very simple initially, but actually can be very complicated for weird numbers, you can instead do synthetic division using that 1. And whatever the result here is actually what the polynomial is evaluated at 1. So like I said, we're going to go ahead and prove this theorem. This is a course you're likely or should be in either college algebra or pre-calculus. We usually do this in pre-calculus at our college. So let's go ahead and get you used to a proof. Now in a proof, you always start with you often, depending on proof style, you often start with the if part, and you want to arrive at the then part. And the if part is called the precedent, and the then part is called the antecedent. So we are going to assume the precedent. We get to assume that we have a polynomial and that we're going to divide it by x minus c. So I'll write that in here. So far, so good. I've just stated the if part. We have a polynomial, we're dividing it by x minus c. Now our goal is to say somehow via deductive logic that the remainder must be p of c. As with any proof, you cannot just grab an example and say, see, it works, because that shows it works with this one example. You want to show that that logic works with all polynomials and all divisors x minus c. So let's go ahead and keep it general here. Now, what do we know? When you go to prove things, you generally try to stick with theorems and definitions. Specifically, we really try to stick with recent theorems and definitions, at least as you're learning mathematics. As you become more proficient with mathematics, then you start reaching deeper into your history of math and grabbing those tools that you might have forgotten about, those rusty tools that you forgot about a long time ago. But for right now, we have a recent statement that we can use, specifically the division algorithm. So by this division algorithm, we can say, if we have a polynomial, which we're stating we have, and we divide it by x minus c, the division algorithm tells us that division will leave us with a polynomial q of x, which we call the quotient, plus some remainder over x minus c. And we're going to state some things about that quotient and that remainder right now. So I'm just stating that q has to be a polynomial, and the degree of our r of x, our remainder, has to be less than 1. And if you don't know that, I'm just going to again rewind the tape here and bring back the division algorithm, and I'm going to highlight a part of that division algorithm that's incredibly important for our conversation right now. The degree of r is either 0 or a degree less than the degree of the divisor. Well, the divisor in the case that we're considering right now with x minus c, that divisor has a degree 1. It's a linear factor. It has degree 1. So if our remainder has a degree less than that, it must be degree 0. If it's degree 0, it's just a constant. And that's what I state here. R of x is no longer a function of x, it's just a constant. It's just some number. But not only that, if we multiply both sides of this equation by x minus c, we'll get the following. Let me back out a little bit. P of x, our polynomial, if you multiply both sides by x minus c, is just going to be q of x, that polynomial, times x minus c, plus the remainder, which is just a constant. Well, now let's take a look at what P of c is. And this is where we really get to our result. So I'm going to say thus, P of c is equal to, well, Q of c, right? Everywhere you see an x, you're just going to replace it with a c. But you can tell right now that c minus c is going to be 0. 0 times anything is 0, And so this will turn into just r. That is, P of C is the remainder when P of X is divided by X minus C. And that is the proof of the remainder theorem. QED, which means quod erat demonstratum, which means so it has been demonstrated. And this is what you want to do in mathematics. You want to attain that level of rigor so that you can prove things without a shadow of a doubt, or beyond the shadow of a doubt. There we go. It's a beautiful theorem. So let's go ahead and use this remainder theorem to evaluate a polynomial. Obviously, you could plug -1/2 into this polynomial, but let's do this more creatively. And by the way, I'm just telling you very honestly, this theorem is incredibly powerful. It allows you to evaluate polynomials that you normally would be frustrated with evaluating. You could do them very quickly using division by x minus the -1/2. So in this case, use remainder theorem to evaluate this for the function p of x equals blah, 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 right? Well, again, we'll take p of x here and we'll divide that by x minus a -1/2. Now, obviously, I don't want to do that long division. I want to do it synthetic division. And all we really need here is the remainder. So I don't care what this piece is. I care what the remainder is, the numerator here. So let's go ahead and do long division, or synthetic division, I apologize. So again, I do this with a -1/2. I steal the coefficients. So we have a 4 on the x cubed. We have a -8 on the x squared. We have a 0 on the x. Be very careful about that. And a 5 as the constant. Bring down the 4. Remember, you're going to be adding in a moment. -1/2 times 4. Well, that's a -2. Add those two up, you get a -10. Let's see. -1/2 times -10 is a +5. Add those up, you get a 5. -1/2 times 5 is a -5/2. And 5 minus 5/2, or plus a -5/2, is 5/2. This is the remainder, and so therefore, p of -1/2 is equal to an actual 5/2. That's exactly what you would have arrived at had you plugged in a -1/2. And if you think about the amount of work required to do this type of computation with the synthetic division versus actually plugging in a -1/2, well, you have a 4 times a -1/2 cubed, so I know I have to apply powers. If powers are your weakness, well then, this is not the way to go. -8 times a -1/2 squared plus 5. And then you go to doing your mathematics, right? 4, this is times a -1/8, -8 times a +1/4, plus 5, and then you say, oh, 4 times a -1/8, that's a -1/2. -8 times 1/4 is a -2, plus 5. So let's see, that's 3 right there. -1/2 is 5/2. I get to the same answer. One's very traditional, that's the blue ink, and one is new, and that's the black ink. And that's the one that you want to sort of focus on in this lecture. Such a good way to evaluate polynomials at specific values. Now, obviously, I think this is so important that I'm actually doing a second example. Generally speaking, one example is pretty good with the remainder theorem, but this is a great example right here. Imagine that you were to plug 2 into this function. You have 6 times 2 to the 4th minus 2 cubed minus 15 times 2 squared plus 2 times 2 minus 7. And you have a lot of powers. Things kind of power up very quickly. Versus synthetic division. So I want to divide this polynomial by x minus 2, essentially, and I want to find the remainder. Well, to do that, I will just do synthetic division using the 2, same as that 2 right there, and I'll write down the coefficients, 6, -1, -15, 2, and -7. Be very, very careful that you're paying attention to the fact that you need to have every power represented. 4, 3, 2, 1, and then the constant. Bring down that 6, 2 times 6 is 12, minus 1 is 11, 2 times 11 is 22, minus 15 is 7, 2 times 7 is 14, 14 plus 2 is 16. I should not have to pause on that. And then finally, what do we have? 2 times 16 is 32. 32 minus 7 is 25. So again, here's our remainder. This tells me that P of 2 is simply 25. Very, very nice. Again, I just wanted to showcase that. That's a very nice way to do this problem. And actually, I don't have it as an example, but I'm going to throw an extra example in here. So let's suppose we have a different polynomial. Let's say it's, I don't know, x cubed minus 2x squared plus, excuse me, x minus 2. And I said evaluate that at 2. P of 2 is equal to. Now I get it that you could just plug in 2. But remember, we're focusing a little bit here on the remainder theorem. So let's go ahead and just evaluate this using the remainder theorem. 1, negative 2, 1, negative 2. Bring down the 1. 2 times 1 is 2. Add those together, it's 0. 2 times 0 is 0. Add those together is 1. 2 times 1 is 2. Add those together, and you get this fantastic 0. So this is kind of nice. This tells us that P of 2 is 0 because that's the remainder had you divided P of x by x minus 2. It would have been some polynomial, specifically 1x squared plus 0x plus 1, and then plus no remainder. Basically, I'll write that in blue, plus 0 over x minus 2, but nobody would write that. 0 over anything is 0. Well, 0 over anything that's non-zero is 0. So that's kind of nice. It's a really nice way to showcase that you don't have a remainder. All right, so now let's move into the factor theorem here. This is actually, the remainder and factor theorems kind of go hand in hand. The remainder theorem is great to allow you to evaluate a polynomial at a given number c. And the factor theorem kind of uses the remainder theorem a little bit in its proof, but also the factor theorem is very, very powerful as well on its own. And this is the factor theorem. It just says that if you know that C is a 0 of P, well, maybe I should say it this way. C is a 0 of P if and only if x minus C is a factor of P. So the words if and only if are very important in mathematics. They're called a bijection. And you'll see people write it this way. If and only if, they'll use 2 F's there. That means if and only if. Another way they will write it is sort of like that implication sign. The first thing implies the second, but it goes both ways. So not only does the first statement imply the second statement, but the second statement implies the first. And that's exactly what a bijection is defined to be, where if P then Q, well, I shouldn't use the letter P because that stands for the polynomial we're working with, but bijection is a very powerful statement. So really this bijection is stating two things. If C is a 0 of our polynomial, then x minus C is a factor of our polynomial. And it's also stating that if x minus C is a factor of the polynomial, then C is a 0 of P. We'll go ahead and start with the proof of this to be mathematical, because this is for a pre-calculus course, and it's always good to see these proofs. So I'm going to prove both of them, both parts of that bijection. So we'll start with this top piece. We'll assume that C is a 0 of P, and we'll want to arrive at, through logical deductive methods, that x minus C must therefore be a factor of our polynomial. So let's go ahead and start that proof. We're going to suppose that C is a 0 of P. And from there you use a little bit of definitions and theorems to help you out. So I want to arrive at that blue highlighted area over there. So let's see, do we have any knowledge of what it means for something to be a 0 of a polynomial? Well, yeah, we actually do. If C is a 0 of P, well, then P of C Well, that must be 0. That's just by definition, by pure definition of what a 0 is. If I told you 5 is a 0 polynomial, then of a polynomial p, then p of 5 would have to be 0. So that's definitional. And now I'm going to bring into this conversation a theorem that we just learned, the remainder theorem. By the remainder theorem, we can say then that p of x divided by x minus c. Well, remember, the remainder theorem tells us that p of c is the remainder after you divide that polynomial by x minus c. Well, this tells us that the remainder must be 0. In fact, I'll write that clearly. So I hope that makes sense, right? Because remember, remainder theorem tells us that p of c is just going to be the remainder of the division p of x divided by x minus c. And in this case, if we know that c is a 0, then p of c is equal to 0. Therefore, p of x divided by x minus c is some polynomial q plus the remainder of 0. Well, if that's the case, that will imply, and maybe I should label this, I'll call this equation 1. So equation 1 implies, therefore, that p of x must equal, if you multiply both sides of equation 1 by x minus c, it'll look like this. And what I've just stated here is that p of x can be factored into x minus c times some other polynomial. That is, x minus c is a factor of our polynomial p. You can factor it out, so therefore it is a factor. So it implies x minus c is a factor of p. And that, folks, is where we want to arrive at. That's that blue ink up in the upper right-hand corner. So half of our proof is done. Some people, by the way, when they do this, they will, maybe I should do it over here. They do this little box and they'll shade like the top half of it, saying that we've just proved half of this. I actually don't like to do that, but if you want to do that, that's more power to you. You could totally do that. That's not that big of a deal to me. All right, so let's go ahead and assume the other way. And let me zoom in here. I'm going to make some changes here. So now we're going to assume that x minus c is a factor of our polynomial, and then we're going to arrive at, again, through logical deductive arguments, that c must therefore be a 0 of our polynomial. So let's go ahead and do that. We're going to, again, suppose, in fact, maybe I should just do a little line here saying, you know what I'm going to do? I'm going to prove the other direction now. So suppose that x minus c is a factor of our polynomial p. Well, if that's the case, then it should be kind of obvious that p can be written as, well, x minus c times some other factor, which would be kind of the other stuff involved that you didn't factor it out. So I'm going to call that other stuff q just for convenience. But that's a logical deductive statement. X minus c is a factor of that polynomial, so we can factor it out. But this is an implication that p of x is equal to x minus c times q of x plus 0. Now, I know what you're thinking. Why would you even write plus 0? It's because if I divide both sides by x minus c, so here's p of x, divide that by x minus c, equals, divide this first term here by x minus c, and you'll just end up with q of x, and divide 0 by x minus c, which you know that's just going to be 0, right? So this implies p of x over x minus c is just some polynomial, but with a 0 remainder. So when I divide p by x minus c, I end up with a clean polynomial with a 0 remainder. And that's critical, because if you have no remainder, that means that if you plug c by the remainder theorem, if you plug c into the polynomial, you should get that remainder, which is 0. which implies, by definition, C is a 0 of P. And remember what we wanted to prove. Up in the, wait for it, upper right-hand corner, we want to prove that blue statement that C is a 0 of P, and that's exactly what we did. So we have proven both statements. The injection and the surjection, you don't need to know those words. We just basically proved the if and only if. We proved it forwards and backwards. That's how most students would think of that. And so I'll just end the proof. QED. Quod erat demonstratum. So it has been demonstrated. So how can this be used? Well, the factor theorem actually gets used in a lot of different places, but here's kind of the initial intro to kind of using the factor theorem here. If I'm in a polynomial of degree 6 that has zeros -5, 0, 3, and 17/3, we'll start there. So by the factor theorem, if the zeros are -5, 0, 3, and 17/3, then we know x minus a -5. So maybe I should write that out actually. -5 is a 0. By the factor theorem tells us x minus a -5 is a factor. 0 is a 0 means that x minus that 0 is a factor, and 3 is a 0 tells us that x minus 3 is a factor, and finally 17 over 3 is a 0 implies that x minus 17 over 3 must be a factor. So I already know our polynomial sort of. Now it doesn't exactly equal this, so I'm going to say it's approximately equal to like an x minus a -5 or x plus 5 times x minus 0, which is just x, times x minus 3, which is just x minus 3, times an x minus 17 over 3, sorry. But that is not enough power. If you were to actually multiply that out, that would only get you to a 4th degree polynomial. And we were told we want to find a 6th degree polynomial. And sorry, my screen is doing that. But then they provide us with a couple more pieces of information. Both 0 and 17 over 3 are zeros with multiplicity 2. And we have already talked about multiplicities of zeros. That was in a previous lecture. I think that lecture was titled Zeros of Polynomials and Their Multiplicities. So we know that the degree of those factors are going to be 2. The degree of the factor x should be 2, and the degree of the factor x minus 17/3 should be 2. So now I don't need to say p of x is roughly equal to that. I can just say p of x is equal to that. There's a polynomial of degree 6 right there, right in front of you. I'll zoom in on that, where it has the zeros -5, 0, 3, and 17/3, and x is of multiplicity 2, and 17/3 has multiplicity 2 as well. Now, obviously, you would not write x like that. Normally, people would write this polynomial this way: x squared times x plus 5 times x minus 3 times x minus 17 over 3 squared. So you would not write parentheses around that x itself because, well, it just looks silly. But anyhow, that's how you could do that. You could build polynomials now. If somebody tells you, I know these are the zeros, now you know the factors. And if they tell you the multiplicities of those zeros, you can now put powers on those factors. And our final example, which is kind of crazy because the remainder and factor theorems end up being so powerful, but this is just an introduction to the remainder and factor theorems. And so we're going to use them heavily in future material, future videos. But for right now, it's good enough that we kind of get a general understanding of how this works. So factor the polynomial below this polynomial p of x. I'll highlight it here. Factor this polynomial. Now, if I just said factor that, most people would just stare at that blankly. You can actually kind of see every single term has an x in common. So you could totally factor that out. But once you factor out that x, and you know what, I'll go ahead and do that. Let me zoom in and it'll probably make my screen go wiggly for a moment. There we go. Once I factor out that x, very simple to see that you can do that. You'll end up with 2x to the fourth plus x cubed minus 20x squared plus 29x to the first minus 12. And then I say, nope, you're not done, because you can factor that further. Most people would stop and stare at this if they have not seen the theory behind the scenes. Remember, you've gone through all of algebra being asked to factor over and over again, but you've never faced something like this. So how do you continue the factorization process? Well, there's actually several things you could do, but luckily somebody was kind enough to say, hey, by the way, x equals 1 is a 0 of multiplicity 2. Point that out. X equals 1 is a 0 of multiplicity 2. That is, x minus 1 squared is a factor. So we should be able to factor out an x minus 1 squared out of this polynomial. Now, how do you do that? Well, there's a lot of different ways that people will do this. The most common, honestly, is long division. That's how most people would do it. But I would like to do a faster way. So let me showcase the best way to do this. If I told you that x equals 0 is a 0, easy fact to see, and that x equals 1 is a 0 of multiplicity 2, then you know that x minus 1 squared is a factor. And you need to know what happens after you divide out x minus 1 a couple times. Well, guess what? If you want to divide out x minus 1 out of, let me use a different color highlighter. This guy right here will work. If you want to factor an x minus 1 twice out of that, synthetic division. Synthetic division will be the fastest way. Remember, dividing that polynomial by x minus 1 is the same thing as performing synthetic division using 1. And now write down the lead coefficients, or the coefficients, 2, 1, negative 20, 29, and negative 12. Let's see what happens, what you get when you divide that polynomial by a negative 1, or x minus 1. Well, you bring down the 2. 2 times 1, that gives me that 2. 2 plus 1 right here. Actually, I'm pointing with my pen, but you can't see that. 2 plus 1 is equal to 3. 1 times 3, well, that's going to be 3. Let me use a different color. Negative 20 plus 3, well, that's easy. Negative 17. 1 times a negative 17, that's a negative 17. And I wanted to still use my green there, but I just didn't. So negative 17. 29 plus a negative 17, which is basically 29 minus 17, is what is that? 19, 12. And then 1 times 12 is 12. I, again, wanted to use green there. You add those up, and you get no remainder. Wow. Well, you obviously shouldn't have a remainder because x minus 1 divides in. So there should be a 0 remainder there. This means that after you've divided this blue highlighted polynomial once by x minus 1, you're left with the polynomial. Let me just showcase this here. If I only divided by x minus 1 once, you'd be left with the polynomial 2x cubed, you reduce the power of x by 1, plus 3x squared minus 17x plus 12. And then I told you that it would actually divide out twice, didn't I? That was in the problem. X equals 1 is a 0 of multiplicity 2, so x minus 1 should divide out twice. Well, you would use these coefficients, I keep wanting to say lead coefficients, but you'd use those coefficients in yet another synthetic division by 1. And here's how I'm going to do it. Rather than rewriting the whole thing, I'm going to do this. Those coefficients were bought or borrowed from these numbers here, 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 and here, weren't they? So instead of writing in this parenthesis 2x cubed plus 3x squared minus 17x plus 12, I'm going to go ahead and perform yet another synthetic division. I'll do this in blue, maybe, on this new polynomial. Let's see what happens when you divide by x minus 1 yet again. I'll bring down that 2. 2 times 1, well, that's 2. Plus 3 is 5. 2 times 5 is 5. Negative 17 plus 5 is a negative 12. 1 times a negative 12. What did I say? 2 times 1? Hold on. Let me say that again because I think I said something wrong there. Bring down the 2, it's 2. 1 times 2 is 2. 2 plus 3 is 5. 1 times 5 is 5. Negative 17 plus 5 is a negative 12. 1 times negative 12 is negative 12. And guess what? No remainder. And now, remember, this was supposed to be a 2x to the 4th. This will be a 2x cubed. This will be a 2x squared. So if I divide out x minus 1 a couple times, I'm left with the quadratic 2x squared plus 5x minus 12. And we know how to factor quadratics. So let's go ahead and do that. I'm going to have to move this over here if you don't mind. So this equals x times x minus 1 quantity squared. I just need two numbers that multiply to 2x squared, which is obviously a 2x and an x, even though I wrote that as a 2. And then I want the back end there to be two numbers that multiply to a negative 12. So it's either a 3 and a 4. I'm going to say it's a 3 and a 4. So let me just double check my work. If this was a 4 and that was a 3, outers would multiply to 8x, inners would multiply to 3x. So 8x and 3x can be combined if it's a positive 8x and a negative 3x. Those can be combined to become that positive 5x there. I don't need to tell you how I did that because you are experts now from years and years and years of factoring, but here you go. Notice the polynomial, which was an impossible looking 5th degree polynomial. And again, I really have to apologize about the scrambled screen. That's just a product of being in COVID and everybody being online. So before, you would never be able to factor a 5th degree polynomial. But if somebody's kind enough to tell you, oh, by the way, x equals 0 is a 0, so you factor that out, and x equals 1 is a 0 twice, multiplicity 2, then you can use synthetic division, like we did, to do synthetic division twice by 1. Here's the first time, and then here's the second. Once you do that, you end up with a beautiful quadratic 2x squared plus 5x minus 12 that you can easily factor, and you get down to this beautiful full factorization of that quintic is what we'd call that. And by the way, that's where we're heading, is to do full factorizations of polynomials. So that's what the next video will kind of step into. We're going to actually probably do some graphing first, but we're going to tie everything together and eventually do some big factorizations. But that's it for this video.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.